In this video, let us learn how to set up a dual polarized antenna, phased array antenna setup in SystemVue phased array design kit. Let us start with the configuration or the geometry of the phased array antenna here. We are configuring a 4x4 antenna array with a dual polarized antenna. The way it is done is we assume there are two antennas at the same location, one responding to different polarizations. We have one set of antennas in the odd number of rows as one type of polarization. It can be E theta. The other rows, the even rows, will be the antennas with other type of polarization, which can be E phi. These polarizations can be right circular polarization or left circular polarization. It is the prerequisite for this one is we have simulated the antenna array in an electromagnetic tool, or we simulated this in a or we measured the antenna patterns in an anechoic chamber. Either way, we assume that we collected all the 32 element embedded patterns and then brought them into a single directory in the computer. Then in SystemVue, it maps these files onto the elements. The convention in SystemVue is that the bottom left corner element is the first element. So the file number 1 will go to the bottom left corner element. So it is imperative that in the simulation where these element patterns were simulated in the electromagnetic tool, the geometry is such that the bottom left corner is the beginning element, and the file number 1 is the antenna pattern file of that element. Can we have a different configuration in the electromagnetic tool and then bring it into SystemVue and then map it differently? Yes, it is possible, but for today, let us keep it simple, assuming that the same pattern, that the same geometry that we defined in electromagnetic tool conforms to the same convention in SystemVue. Now, how do we set it up in SystemVue? Let's open up the array antenna properties, and as we can see, we defined a 4x4 array with half lambda spacing here, and then we have two antennas per location. For defining the element patterns, we chose the pattern type is the pattern file, and then it came from an electromagnetic tool, EM Pro. EM Pro is a Keysight electromagnetic simulation platform. We can also bring from other tools as shown here. And we are assuming that all the embedded patterns are unique. So we chose the option individual for each element. And we have to just specify the first file since all the files have to be indexed as shown here. Once we specify the first file, rest of the 31 files will be picked up by the simulator automatically. If we want to examine if the files are going to be read properly by the or not by the tool, we can just enter the index and then check the pattern by pressing display pattern. As we can see, every alternate pattern will belong to a different polarization. Now, having checked that the pattern files are okay, properly specified, we move on to the receiver property where we define the frequency, we define the power density in terms of dBm per meter square, incident at the input of the antenna array, and also the polarization of the incoming wave in terms of E theta and E phi components. To begin with, let us define that all the wave is only E theta polarized. Once we define this, the antenna will produce 32 outputs that will go through a 32 amplifiers, and then that will go through 32 phase shifters. The phase shifter will compute the phase shifts required to produce the beam in the direction entered here. So there will be 16 phase shifts for each of these polarizations. There's each the two rows will be identical, each row corresponding to the one type of polarization. Um, so all the even rows and all the odd rows will have the same identical phase shifts that will be applied to the antenna elements. Then the 32 signals will go through 32 attenuators, and then they go through a combiner that will combine all the even numbered elements into one output, all the odd numbered element outputs into another output. So there will be two outputs at this output of this first combiner. The second combiner will combine both these outputs and send the signal into the receiver where further processing will take place. Let us examine, having set it up like this, let us examine what will be the output from the first combiner. And um, before we simulate, let us try to guess what that would be. Since the incoming wave is all E theta, we expect that the output from the first combiner will only be a E theta output and no E phi output. Let us see if that is the case. If we simulate and then examine the data set, we will see that uh, it produces a lot of outputs, a lot of information is provided. Let us go and then examine the node information, and especially the signal output, signal power from the array split 1 or array combiner 1. As we can see, the E theta antennas together have only produced some output, and the E phi antennas produced a very low output. So the question here is that we should not actually ideally see any output from the E phi antennas because the incoming wave has no E phi component, and the E phi antennas ideally should pick up only E phi and not E theta. But since here the antenna is a practical antenna, it's not an ideal mathematical antenna, it will have some kind of a response even to the other type of polarization, even though it is very small. That is why here the E phi antennas were able to pick up a small values, small contribution of E theta and then produce an output here. This represents a more practical situation. Now, in order to verify if our antennas, the E phi antennas, are also going to respond to an incoming wave, we can reverse the polarization of the incoming wave and see what happens. Now you see that the roles are reversed. The E theta antennas together produced very small, very low output, whereas the E phi antennas produced the correct expected output here. So from this, we can see that we have very successfully defined a dual polarization in the system. But the question is, can we actually form different beams on the different polarizations, and can we send them to different receivers for processing, etc.? Yes, all that can be done, but we will cover that in another video that will be defined in a combination of frequency domain as well as time domain setup for the phased array. Before we end, let us examine the phase shifts to get a feel for what kind of how the phase shifts are generated by this phase shifter. If we go into the data set again and then look at the part information and pick up the phase shifter information, the phase shifter has produced 32 phase shifts. If we examine every consecutive phase shifts are identical. So what it means is 16 of them are for one polarization and the other 16 is for the other polarization, but both these polarizations are transmitted or received in the same direction. Thank you very much for watching this video, and look out for coming up videos on advanced setups for the polarization in phased arrays.